Have you ever looked up at the moon and, thought you basically knew its whole story?
Like the standard narrative. Ancient fire then?
Right.
Quiet.
Exactly. Fiery beginnings, cooled down ages ago, now just sort of there, silent.
Well, hold that thought.
Oh.
Because there's this rock, just one rock found right here on Earth, and it's adding a whole new chapter.
A hidden chapter. About the moon's past.
Yeah, suggesting things were maybe a lot more dynamic for a lot longer than we figured.
Okay, I'm intrigued. So today, we're doing a deep dive into that. This rock.
We are. It's a lunar meteorite, officially called Northwest Africa 16286. NWA 16286 for short.
And you're saying this single rock is changing how we see the moon's volcanic history and its internal heat.
Pretty much. We'll get into where it came from, why its age is such a big deal, and what its specific chemistry tells us.
About lunar processes we thought had stopped billions of years ago.
Exactly. Prepare for maybe a bit of a, okay moment about the moon.
All right, let's get into it. So, the star of the show. Northwest Africa, 16286. It's not huge, right? About 311 grams.
That's right. Just 311 grams. Found in Africa back in 2023.
And finding a piece of the moon here on Earth is rare, but this one's even rarer.
Oh, definitely. It's a specific type of lunar rock, a basalt, a volcanic rock.
Okay.
And it's only one of about, 31 lunar basalts ever officially ID'd on Earth?
Wow. So out of all the meteorites hitting us, getting a volcanic piece of the moon is really, really uncommon.
Extremely. And that's why these lunar meteorites are so valuable. Dr. Joshua Snape at Manchester University really highlights this point.
Right, because we spent so much effort, Apollo, Luna, the Chang'e missions.
Yeah.
Going to specific spots to grab samples.
Exactly. Those missions are incredible, giving us super detailed info about tiny areas. But they're just tiny areas.
Whereas a meteorite...
It could come from anywhere. A big impact hits the moon, blasts rocks off the surface randomly.
And some of that debris eventually finds its way here.
Precisely. So NWA 16286 is like this free sample, potentially from a part of the moon we've never visited, a serendipitous piece of lunar geology, basically.
Okay, so here's where it gets really interesting, you were saying. The age.
Yeah, this is the core of it. They dated its solidification when it cooled from magma into rock at around 2.35 billion years ago.
2.35 billion. Now, why is that number so significant?
Because for a long time, based mostly on the Apollo samples, the thinking was that major lunar volcanism kind of wound down much earlier. Maybe, around 3.2 billion years ago.
So there was this massive gap, like almost a billion years, where we didn't have much physical proof of volcanoes erupting.
Exactly. A huge dark period in our understanding. This meteorite lands smack dab in the middle of that gap.
Wow, okay.
It tells us pretty definitively that the moon was still volcanically active during that time. It's like finding a lost chapter, like you said.
So just to place it, it's younger than a lot of the Apollo rocks. Younger than Chang'e 6's recent samples.
Right.
But older. Quite a bit older than the very young rocks China's Chang'e 5 mission brought back a few years ago.
Correct. It bridges that gap beautifully. It shows this wasn't just an early burst of activity that died off quickly. The moon kept going.
So this one rock basically forces us to rethink how long the moon stayed geologically active. It extends that known period quite significantly.
It really does. It challenges that picture of the moon cooling down and becoming sort of geologically quiet so early on. Its internal engine was still working.
Okay, and the rock itself holds clues about how it stayed active.
Right.
Let's get into the chemistry. What's its fingerprint tell us?
Well, looking at its composition, it's what we call an olivine ferric basalt. Meaning it's volcanic. And it has these fairly large, noticeable crystals of a mineral called olivine embedded in it.
Okay.
It also has moderate titanium levels, but interestingly, high levels of potassium. That specific mix gives us hints about where it formed deep inside the moon.
You mentioned isotopes earlier, specifically lead isotopes.
Yeah.
How do those act like tiny clocks?
Yeah, the lead isotopes. That's some really clever geochemistry. Isotopes are versions of elements with slightly different weights.
Right.
And the ratios of different lead isotopes get locked in when the rock forms. They don't change, so they act like this permanent fingerprint of the source material.
So what does the lead fingerprint in this rock tell us?
It points to NWA 16286, coming from a source region deep in the moon that had an unusually high ratio of uranium to lead.
Uranium. That's radioactive, right.
Exactly. And radioactive elements like uranium decay over time, and that decay process releases heat continuously for billions of years.
So it's like evidence of an internal heat source, A long-lasting one.
Precisely. The high uranium content suggests a source that was naturally generating its own heat through radioactive decay. Think of it like embers still glowing deep inside.
So these chemical clues, the olivine, the potassium, and especially this uranium-lead signature, it all points to this ongoing heat engine, keeping parts of the moon molten for eruptions.
That's the implication, yeah. It helps explain how a body as small as the moon could have stayed warm enough inside to fuel volcanism for so long, much longer than some models predicted.
It suggests a more complex internal heating process than we maybe gave it credit for.
Definitely more complex and more prolonged.
Now, this rock didn't just gently float down to Earth. You mentioned its journey was rough. What do we see in the rock itself that shows that?
Yeah, if you look at it under a powerful microscope, like a scanning electron microscope, a Huff AM,
Okay.
you see these different shades of gray showing slightly different chemistries mashed together, but you also see these pockets and veins of melted glass.
Melted glass.
Yeah, like parts of the rock got instantly heated to melting point and then cooled rapidly. That's a classic sign of shock.
Shock from what? An impact.
Almost certainly.
Yeah.
The idea is that the original basalt rock was sitting on the moon, then got hit hard by an asteroid or another meteorite.
Right.
That impact melted parts of it, created those glassy bits, and provided the energy to blast it off the moon entirely.
So it got flung into space, traveled who knows how long, and eventually landed here. That impact history must make dating it trickier, though.
It does add complexity, yes. Shock events can sometimes reset or disturb the isotopic clocks we use for dating.
But they still managed to get that 2.35 billion year age, plus or minus just 80 million years.
They did, which is actually pretty remarkable, given the shock evidence. It really shows how sophisticated and robust these radiometric dating techniques have become.
Amazing precision, even after all that.
It really is a testament to the science.
So let's pull it all together. After digging into its journey, its age, its chemistry, what's the big takeaway? What does this one rock really mean for how we understand the moon?
I think the core message is that it gives us crucial new boundaries, new constraints on when volcanism happened on the moon and maybe how.
It stretches out that active timeline by almost 1 billion years, filling that gap we talked about.
Exactly. It rewrites a big chunk of the moon's geological history, confirming it wasn't quiet during that period. And it hints that there's just, well, a lot more complexity to the moon story than we knew.
Even after all the missions and decades of study.
Even then, there's still so much to learn.
And looking ahead, this rock could actually guide future exploration.
Potentially, yes. If scientists can do more work, maybe figure out roughly where on the moon this rock originally came from.
Like trace it back to a specific region or crater.
Yeah, if they can link its unique chemistry to surface measurements from orbiters, for example, then that region becomes a really high priority target for future sample return missions.
Because we know interesting things were happening there, geologically speaking, at that specific time.
Precisely. It helps us target our search for more answers much more effectively.
That's incredible. And this is fresh science, right?
Yeah.
Just presented.
It's very fresh. The University of Manchester team unveiled these findings at the Goldschmidt Conference in Prague recently. It's funded by the Royal Society, and they're aiming to get it published in a peer-reviewed journal later this year. So we're talking right at the cutting edge.
Fantastic. So just to recap for everyone listening, you've basically heard how one meteorite, NWA 16286, found in Africa, has seriously expanded our view of the moon.
Yeah, showing its volcanic heartbeat for much longer than we thought, pushing back that timeline by potentially billions of years.
It's a great reminder, isn't it? That even our closest celestial neighbor, one we think we know so well, still holds some pretty deep secrets.
Absolutely. It makes you wonder, doesn't it?
What specifically comes to mind for you?
Well, just thinking, if this one unexpected rock can tell us so much about the moon's hidden heat and extended volcanic life, what other big assumptions might be out there?
About other planets? Or moons?
Yeah, about how planets form and evolve throughout the solar system. What other knowns might be overturned by the next unexpected find? What other huge gaps in our timelines are just waiting for the right piece of evidence, maybe lying undiscovered right now?
That's definitely something to think about. What secrets are still out there, maybe closer than we think?